In this video, I will be discussing about substitution suggested by the given differential equation. A differential equation of the form m of x and y dx plus n of x and y dy, which is equal to 0, may not yield a solution obviously using the methods we have previously discussed in the previous videos. However, it may be possible to change some of the variables of the given equation to a form we know how to solve. So let's take an example here. Find the general solution of this differential equation. Now, looking at this differential equation, we notice that there are some terms that are similar to each other, like this 3x and 2y here, the same with this 3x plus 2y. So in this situation, we are given the hint of replacing these similar terms into a one variable. So to solve this one, let us use, say, a variable z, and z is the representation of this 3x plus 2y. And if we're going to find the differential of this z, this is equal to 3dx plus 2 dy if you take the derivative implicitly here. Now, suppose we solve for the dx. What you will do is to subtract both sides of the equation by 2 dy. So we have dz minus 2 dy, which is equal to 3 dx. So the 2 dy at the right will be cancelled, but I have the minus 2 dy at the left. So therefore, our dx, when you divide both sides of the equation by 3, is equal to dz minus 2 dy all over 3 here. So this is our representation of our dx, and this is our representation for 3x plus 2y. So looking at our differential equation, instead of writing 3x plus 2y, we will write its representation, which is z. So this is z plus 4, because we have a 4 here, times dx, and we have our representation of dx here. So instead of writing dx there, you will write dz minus 2 dy over 3, and this is added to, again, this 3x plus 2y, which is z, minus 3 times dy, which is equal to 0. Now, looking at this resulting equation, the equation is now in terms of two variables, z and y. So, to eliminate this denominator of 3, let us multiply both sides of the equation by 3. So, we have z plus 4 times the quantity of dz minus 2 dy, because this denominator will be cancelled by this 3 here, and this is added to 3 times z minus 3 dy, which is equal to 0, because 0 times 3 is 0. Now, simplifying further by multiplying this binomial to this binomial here. So we have z plus 4 times dz, and we have also z plus 4 times 2 dy here, and this is added to 3 times z minus 3 dy, which is equal to 0. So distributing this 2 dy to this binomial, and also this dy to this binomial here, we have z plus 4 times dz minus 2z dy minus 8 dy, because 4 times 2 is 8 dy, but we have a negative here, so that's why negative 8 dy. And this is added to 3z dy minus 9 dy, which is equal to 0. Now, let us combine similar terms here. This one, minus 2z dy, and this 3z dy here. So, we have z plus 4 times dz, and we have this plus 1z dy, and this is minus 17 dy here. So factoring the common factor, which is dy, we have z plus 4 times dz plus z minus 17 times dy, which is equal to 0. We notice that this is already a separable differential equation by moving the z minus 17 as the denominator of this term here. And that can be accomplished by multiplying both sides of the equation by 1 over this z minus 17. So we have z plus 4 over z minus 17 dz plus dy, which is equal to 0. And we notice that we can now integrate each term in this equation. So no problem with the dy, it's very easy to integrate, but we need to simplify this fraction because this fraction is an improper fraction. Why? Because the degree of the numerator is 1, which is equal to the degree of the denominator, which is also 1. So therefore, we need to divide the numerator by the denominator here. So if we are going to divide our z plus 4, our numerator, by the denominator, which is z minus 17, we have z divided by z, it's 1. And 1 times z, it's z. And 1 times negative 17 is minus 17. So subtracting each column here, we have z minus z, it's 0. So this cancels. And 4 minus the negative 17 is positive 21. So therefore, this fraction here can be rewritten as 1 plus 21 over the denominator z minus 17, and the whole thing will be multiplied by dz plus the dy, which is equal to 0. So distributing this dz to this binomial, we have dz plus 21 over z minus 17 times dz, and this is added to dy here, and the whole sum is equal to 0. We notice that we can now easily integrate each term here. So we integrate dz, also integrate this term here. So this is 21. When we factor the 21 in front of the integral symbol, so this is the integral of dz over z minus 17 plus the integral of dy, which is equal to the integral of 0. So integrating dz is z here plus 21 times the natural log of z minus 17, because if you let this denominator z minus 17 as your u, the du of this denominator is dz, which is found there in the numerator. And the integral of dy is also y. And this is equal to the constant of integration c. So substituting back our original variables, our representations of z, which is 3x plus 2y. We have 3x plus 2y plus 21 times the natural log of our z, which is 3x plus 2y. That is the value of z, and we subtract 17 here plus y, which is equal to the constant of integration c. So combining these similar terms here, 2y and y, so we have 3x plus 3y here. So we just factor 3 outside there, and this is added to 21 times the natural log of 3x plus 2y minus 17, which is equal to the constant of integration c. And we notice that each term here in this equation are divisible by 3. So we can reduce this one by multiplying both sides of the equation by 1/3. So we have the final answer as x plus y plus 7 times the natural log of 3x plus 2y minus 17, which is equal to the constant of integration c. And we say that this is our solution to the given differential equation. So as you go back to your solution, the equation itself suggests that we need to represent this binomial that appears twice in the equation by some variable z here to simplify the differential equation in finding the solution. Now let's proceed to our example number 2. Find the general solution for this differential equation. Now, looking at our differential equation, we notice that there are no parts in it that are repeating. But we notice that this x plus y can be simplified by representing that one by a single variable, say z. So let z be equal to x plus y, and finding the derivative of this equation implicitly, so this is dx plus dy, the value of our dz. Now, looking at our equation, we notice that the multiplier of dy, which is understood to have a 1, is simpler than the multiplier of dx. So therefore, it gives us a hint that we will be solving for dy. So solving for dy here, we need to subtract both sides of the equation by dx. So we have dz minus dx is equal to dy. So this is our representation of dy, and this is also our representation for x plus y. So looking at our differential equation, we can substitute our dy here by our representation, which is dz minus dx, and this is subtracted by our sine z, because instead of writing x plus y, we will write its representation, which is z, and this is multiplied by dx here. So combining similar terms, because we have a dx here and we have the dx also here, we have dz minus 1 plus sine z times dx, and the whole expression is equal to 0. And we notice that this is already a separable differential equation. So to solve this separable differential equation, we will move this 1 plus sine z as the denominator of dz. And we can do that by multiplying both sides of the equation by this binomial, which is the 1 over 1 plus sine z. So multiplying this one to dz, we have dz over 1 plus sine z. And this is subtracted by just dx. And the whole expression is equal to 0 because 0 times this fraction is 0. Now, it seems to be tricky to integrate this fraction here, but you can recall from your previous calculus that we can multiply this fraction by the conjugate of its denominator. So the conjugate of the denominator is 1 minus sine z. And if that is the one that you multiply to the numerator, the same also in the denominator, so that you will not alter the value of this fraction. And as a result, we have 1 minus sine z dz divided by the difference of two squares, which is 1 minus sine z quantity squared. And this is subtracted by dx here. And applying our knowledge in trigonometric identities, we know that the denominator has an identical expression, which is equal to cosine squared z. And we need to subtract this one by dx here. So separating this binomial into two fractions, we have 1 over cosine squared z dz minus sine z over cosine squared z dz minus dx, which is equal to 0. And integrating each term in the equation, we have the integral of 1 over cosine squared z dz minus the integral of cosine z to the power negative 2 if you move this cosine squared z to the numerator, and this is multiplied by sine z dz minus the integral of dx, which is equal to the integral of 0. And we know by identities that this is just equal to secant squared z. And you notice also that by substitution, if this is your u, which is cosine z, the du is not sine z dz, but it's negative sine z dz. So I will provide there a negative for the sine z dz. But maybe you will ask, where did I get this negative 1? I need to neutralize this negative by multiplying negative 1 outside the integral symbol. So that negative 1 times negative is positive, and this is subtracted by the integral of dx, which is equal to the integral of 0. Now, we can integrate them one by one. We know from your previous calculus that the integral of secant squared is tangent z, and this is plus 1 times the integral of cosine z to the negative 2, which is cosine z to the power negative 1 over the negative 1 using the power rule. And this is subtracted by the integral of dx, which is x, and the integral of 0, which is c. So we have tangent z minus the reciprocal of cosine z, which is secant z here. And this is subtracted by x, and the whole expression is equated to the constant of integration c. And substituting our original variables for z here, we have tangent of x plus y, because our z is x plus y, minus secant of x plus y minus x is equal to the constant of integration c. And we say that this is our solution for the given differential equation. Now let's proceed to our example number 3. Find the general solution for this differential equation. Now, looking at this differential equation, we might suspect that we can represent this trinomial here. So let us try representing that trinomial as z. So we have z equals 9x plus 4y plus 1. And solving for the differential of z, we have 9dx plus 4dy. And solving for dy, we need to move this 9dx by subtracting both sides of the equation by 9dx. So we have dz minus 9dx, which is equal to 4dy. And dividing both sides of the equation by 4, we have dz minus 9dx divided by 4 is the value of our dy. So this is the representation for our dy when our z is this trinomial. So rewriting this y prime as derivative of y with respect to x, this is equal to 9x plus 4y plus 1 quantity raised to the second power. Now, multiplying both sides of the equation by dx, we have dy, which is equal to 9x plus 4y plus 1 quantity squared times dx. So instead of writing dy here, we will write its representation, which is dz minus 9dx. And this is divided by 4 here, which is equal to z, because this trinomial, we represent this one as our z. And this is multiplied by dx. So, eliminating this 4 in the denominator, we can multiply both sides of the equation by 4. So, we have dz minus 9dx, which is equal to 4z squared dx. And moving all terms to the left side of the equation, we have dz minus 9dx minus 4z squared dx, which is equated to 0. And factoring the common factor of dx here, we have dz minus 9 plus 4z squared times dx. And we noticed that this is already a separable differential equation, because we can move this 9 plus 4z squared to the denominator of dz. And we can do that by multiplying both sides of the equation by 1 over 9 plus 4z squared. So we have dz over 9 plus 4z squared minus dx, which is equal to 0. And integrating each term in this equation, we have the integral of dz over 9 plus 4z squared minus the integral of dx, which is equal to the integral of 0 here. And expressing the denominator of this integrand as the sum of two squares, we have 3 quantity squared plus 2z quantity squared minus the integral of dx, which is equal to the integral of 0. And you notice that this integrand is very familiar to us, because if you let a be equal to 3 and your u be equal to 2z, we notice that the differential of u is 2dz, but we don't have a 2dz here, so we need to divide both sides of the equation by 2. So this is the value of dz here, and this is our u, which is 2z. So substituting to the integrand, we have du over 2. So instead of writing dz, I will write du over 2, and this is divided by a squared plus u squared, because instead of writing 3, I will write a here, and instead of writing 2z, I will write u, because that is our representation there. So factoring outside the integral symbol, we have 1/2 times the integral of du over a squared plus u squared minus the integral of dx, which is equal to the integral of 0. Now we know that the integral of this fraction is equal to 1 over a times the arctangent of u over a, and this is subtracted by x, which is the integral of dx, and this is equated to the constant of integration c. So simplifying our answer, we have 1/2 times 1 over 3, because our a is 3, times the arctangent of our u, which is 2z, and our a, which is 3, minus x, which is equal to the constant of integration c. And multiplying this 1/2 to this 1/3, we have 1/6 times the arctangent of 2 times the z, and our representation for the z is this one, which is 9x plus 4y plus 1, and this is divided by 3 minus x, which is equal to the constant of integration c. And removing this 6 in the denominator, we can do that by multiplying both sides of the equation by 6. So what we have is the arctangent of the quantity of 2/3 times 9x plus 4y plus 1 minus 6x, which is equal to the constant of integration c, because 6 times negative x is negative 6x, and 6 times another constant is still a constant here. So therefore, we say that this is our solution for this differential equation. Now, let's proceed to our example number 4. Determine the general solution for this differential equation. Before we can solve, let us transform this differential equation to its equivalent differential form. So we have dy dx, which is equal to 1 plus 3x times sine y over x squared times the cosine y. So we can simplify this one by multiplying the LCD of the two denominator, which is x squared times cosine y dx. So this dx here and this dx in the denominator will cancel each other. So we have x squared cosine y times dy. And this is equal to 1 plus 3x times sine y, which is multiplied by dx, because this one and this one cancels each other. And looking at this differential equation, we notice that we have two trig functions here. We have the sine y And we have also the cosine y here. And we know from your differential calculus that the derivative of sine y is cosine y. So therefore, it gives us the idea for our representation here. So let z be equal to sine y. So our derivative of z is equal to cosine y. So therefore, instead of writing cosine y dy, I will write dz here. So we have x squared times dz. And instead of writing sine y, I will write the representation of sine y, which is z. And this is multiplied by dx here. And moving all the terms to the right, we have 1 dx. If you distribute this dx to this binomial here, and this is added to 3xz dx minus the x squared dz. And eliminating this x squared, because this is dz here, we multiply both sides of the equation by 1 over x squared. So we have 0, which is equal to dx over x squared plus 3 over x z dx minus dz here. And forming the derivative of z with respect to x, we need to multiply both sides of the equation by 1 over dx here. So this is equal to 1 over x squared. And this is added to 3 over x z minus dz over dx. So moving this term to the left side, we have positive dz over dx minus 3 over x times z, which is equal to 1 over x squared. And we noticed that this is already a first order linear differential equation. So this is now a first order linear differential equation because this is linear in z here. So we have our a, which is this one, and we have our b of x, which is this one here. So therefore, we can find our integrating factor. So the integrating factor here can be obtained by raising our e to the exponent of the integral of a of x dx. And you can recall this one from our previous video about solving first order linear differential equation. So this is e raised to the exponent of the integral of a of x, which is negative 3 over x dx. And therefore, our integrating factor phi of x is e raised to the exponent of the negative 3 times the integral of dx over x. So we have e to the exponent of negative 3 ln x, because the integral of dx over x is ln x. And using the property of logarithms, we have this negative 3 as the exponent of x. So we have e to the power ln x to the power negative 3. And again, by the properties of logarithms and exponentials, we have x to the power negative 3. So this is now our integrating factor. So multiplying our first order linear differential equation by this integrating factor, we have x to the power negative 3 times dz dx. So you multiply that one, minus x to the power negative 3 times 3 over x z, which is equal to x to the power negative 3 times 1 over x squared. And simplifying this equation here, we have x to the power negative 3 times the derivative of z with respect to x minus 3x to the power negative 4z, because this x here, when you move this one to the numerator, it will have a negative 1 exponent. So negative 1 plus the negative 3, we have negative 4 here. And this is equal to x to the power negative 5. And you notice that this one is already a derivative of a product. If you can easily see that one, to shorten our solution, that is the derivative of x to the power negative 3 and z. So this is the derivative with respect to x. And you can check that we have the first factor x to the power negative 3 here times the derivative of z with respect to x plus the z here times the derivative of x to the power negative 3. And the derivative of this is negative 3 times x to the power negative 4 by the power rule. And this is equal to x to the power negative 5. So rewriting this one, we have the differential of x to the power negative 3 times z, which is equal to x to the power negative 5 dx. So integrating both sides of the equation, the answer is x to the power negative 3 times z, because the integral of the differential cancels each other, and by the power rule, this is equal to x to the power negative 4 divided by negative 4 plus the constant of integration c. And to eliminate this 4 here, we need to multiply both sides of the equation by 4. So we have 4x to the power negative 3 times z, which is equal to negative x to the power negative 4 plus the constant of integration c. Because the constant 4 when multiplied by another constant, the result is still a constant. And eliminating these negative exponents here, we need to multiply both sides of the equation by x to the power 4. So we have 4x times z, which is equal to negative 1 plus c x to the power of 4. Then substituting back our original representation of z, which is sine y, we have 4x times the sine y, which is equal to cx to the 4th minus 1. And this is our solution for this differential equation. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.